All right, so we are approaching the end of the course, and we're going to talk about limits. So a limit is a value that a function approaches. So let's start off with these notes over here. And here's a function, f of x, and hopefully my marker starts working, and it's not. Okay, there it goes. So we're going to find all the key features, the zeros, the asymptotes, and the wholes. So this is something we did in the rational functions unit. So, okay, first thing I'm going to do, okay, this is not there, okay. Awesome. First thing I'm going to do is sort of break this down just so I can see it in factored form. So it looks like f of x equals x plus 2 times x minus 2 over, that's going to be x plus 8 times x minus 2. Yeah. Okay. So where are the zeros? The zeros are at x equals -2, and that comes from this term right there. Okay, where are the vertical asymptotes? That's going to be at x equals -8, and that comes from this term right here. Where are the wholes? Wholes are at x equals 2, and that comes from these terms because they are the same on top and bottom. That makes it a whole. So zeros, wholes, horizontal asymptote as well. You know, we could talk about the end behavior here. If I look at the leading term over the leading term, x squared over x squared, so it looks like there's a horizontal asymptote at y equals 1. Okay, so those are the key features. So this is the one we're going to talk about right now. We're going to talk about the whole at x equals 2. If I plug 2 into this function, if I evaluate f of 2, I get an error on the calculator, right? We know that that's because the function's undefined at x equals 2. There is no value. So this is undefined here. Undefined. Okay, but we can kind of like estimate a value by getting really, really close to 2. So I could use a number like 1.9 or 1.99 or 1.99999999, right? I could keep going. I can get really, really, really close to 2. And that's the idea of a limit. So in one hand, we have, I'm just going to say that this is finding the limit as x approaches 2 from the left. And over here, this is the limit as x approaches 2 from the right. So we're going to be talking about left-hand side limits, right-hand side limits. What that means is left being below the number we're talking about and right being above the number we're talking about. Because as we can see from this table, right, 1.99 is very close to 2, but it's just as close as 2.01 is, right? So they're both very close to 2. One is lower than 2, one is above 2. So it's as x approaches 2 from the left, because if we were looking at this on a graph, right, like on the axis we see on the graph here, right, we're approaching 2 from the left, we're coming from this side at 1.99, or we're coming from this side at 2.01, right? Okay. That's the idea of a limit. So how can we fill this in? Well, we can use our calculator. Right, I'm just going to go to y equals, and I'm going to plug in this function. So x squared minus 4 over x squared plus 6x minus 16. And I get the graph of that. And I can hit trace, and I can plug in a value, right? If I wanted to evaluate at 2, I hit 2, and enter, and we see there's no y value because it's undefined, right? But I can do 1.99, and I can get this value of approximately 0.399, right? And then I can do 1.999, and so on. So let's go ahead and finish this table. And what we're going to see is that we get really, really close to a certain number. And okay, 2.01 is 4.01 approximately, 4.401, and then we can keep filling this out. And we get these values that as x approaches 2, as x gets closer and closer to 2, the y value, or the function value, gets closer and closer to what number? What number is this getting closer and closer to? It's getting closer and closer to, looks like 0.4, right? And so this is the idea of a limit. As x approaches k, the value of the function is approaching a certain value, right? If the limit from the left is equal to the limit from the right, then the limit exists. So if I'm looking at the left, it's getting closer and closer to a certain number. Like I can kind of block out the whole right side of that table and just look at the left side, and I can still see that it's getting closer and closer to 0.4, right? I can also block out the whole left side and just look at the right, and I also see it's getting closer and closer to 0.4. Because those numbers are equal to each other, the limit exists, and the limit is 0.4. Okay. In limit notation, we say the limit as x approaches 2 of the function x squared minus 4 over x squared plus 6x minus 16 equals 0.4. Okay, so the limit of the function is equal to 0.4. The function value at 2 is not 0.4. The function value is undefined, right? But the limit, because we have this limit notation here, we can say the limit as x approaches 2 of that function is 0.4. So let's go ahead and try another function. So now we're going to find the limit as x approaches 0 of a function sine x over x. So I'm going to plug that in my calculator. Sine x over x. And I want to be in radian mode. I'm just going to make sure I am. Yep. Okay, there's the graph. I'm going to trace. Okay, obviously if you plug 0 in, you can't divide by 0, right? So that's undefined. But we can see that if we choose numbers close to 0, so for example, what's to the left of 0? What number is really, really close to 0, but to the left of it? That would be in the negatives, so like negative, let's put 0.01, negative 0.001, right? And we can just get closer and closer to 0. Same thing over here. 0.01 is pretty close, but we can get closer. And so on. Okay, so then we fill out those values. -0.01. And we see already at that point we are at 0.9999, right? We're approximately 1, we're approximately 1. That 4 9s and an 8 if we were rounding properly. Approximately 1, approximately 1. But this is undefined. Okay? But the limit as x approaches 0 of sine x over x is 1. Okay, now you might have also noticed that just looking at the graph, well, yeah, it looks like the function value's up there at 1. You can't see the hole, but we know there's a hole there. But it kind of makes sense that the limit is 1 because that's where it should be, right? So we can do limits graphically as well. So here's a function. It's a very interesting function, right? It's got some holes in it. It's got some discontinuity. And yeah, we have some holes, some filled in points and whatnot. So first of all, let's take a look at the limit as x approaches 1 of f of x. So as x approaches 1, so as we're getting closer and closer to this 1, what's happening to the function? Well, if I go up and go really close to the left of it, as I get closer to 1, I'm kind of like doing this from the left. And from the right, I'm coming in closer to 1, right? Because here's this is what I'm talking about. This is x equals 1, right? So as I'm going from the left, I'm getting close to 1. From the right, I'm getting close to 1. Because those are equal, the limit as x approaches 1 is 1, okay? But what's the function value at 1? At 1, I look for the function value. That's an open circle. That's a filled in circle, so the function value is 2. Okay? So make sure you understand the difference there between the limit of a function and the function value. How about the limit as x approaches 4? Again, as I go from the left and from the right, it looks like it's approaching the same value, which happens to be 2. So the limit's 2. What's the function value at 4? It's undefined. Okay, because it's an open circle and then there is no other point at 4. How about the limit as x approaches 2? So as x approaches 2, here's x equals 2. So from the left, I'm approaching this value here, and from the right, I'm approaching this value here. So from the left, it looks like I'm approaching 2, but from the right, it looks like I'm approaching 3. Because those numbers don't match, because they're not the same, this limit does not exist. Okay. The function value at 2, it is defined because there's a closed circle. F of 2 is 2. How about the limit as x approaches infinity? Well, that means end behavior, right? So as we go to the right, f of x, it looks like it's going arrow down, so that's negative infinity. And the limit as x approaches negative infinity, it's arrowing down, negative infinity. Okay, so we can talk about infinite limits as well in the sense of end behavior. It's not as much sense, we're not going to deal too much with infinite limits because that really only means end behavior, and we've already talked about that. So again, we can talk about one-sided limits, right? The limit as x approaches 2 did not exist because the limit as x approaches 2 from the left, so this is the notation for from the left, the limit as x approaches 2 from the left was 2. And from the right, it was 3. And so notice the notation here. That means from the right. That means from the left. Okay, so they'll use a little negative sign for left because it's under the value, or a positive value from the right because it's above the value. Okay, so I would have you guys go ahead and try this first. So pause the video and then unpause when you're ready to check your answers. So the limit as x approaches 6 from the left. So I got to go find 6 and then go to the left of 6 and then approach 6. I'll get close to it. So that is 2. The limit as x approaches 6 from the right, so go to 6, go to the right of it, and approach, that's 5. And so what's the limit as x approaches 6? That does not exist because left-hand limit and right-hand limit do not equal each other. What's the function value at 6? That's 5. What's the function value at negative 2? Negative 2 is 3. And negative 8 has a function value of negative 3. The limit as x approaches negative infinity. So as I go all the way to the left of the graph, that's an arrow up, so that's positive infinity. And as x approaches positive infinity, so all the way to the right, we're going down to negative infinity. The limit as x approaches negative 8. So this is not a one-sided limit, this is just an overall limit. So in that case, you do have to check both sides to make sure it exists. So here's negative 8 on the left. On the right, both of them are approaching negative 6. So there's the limit. The limit as x approaches negative 2 from the left. So the limit as x approaches negative 2 from the left is 3. The limit as x approaches negative 2 from the right, there's like an asymptote behavior at that side. And so that goes off to infinity. And so what's the limit as x approaches negative 2? Does not exist because they don't match up. Okay, so we have seen finding limits on tables, finding limits on graphs, and now we're going to talk about finding limits algebraically. If a function is continuous, finding limits is very easy. If there's no hole and if there's no undefined points, then finding the limits really easy because you can just find the function value. Okay, so for example, if f of x is continuous, then the limit as x approaches c of f of x is f of c. Just plug the value in. So for example, this one, the limit as x approaches 5 of x plus 9 is going to be 14 because 5 plus 9. I can plug 5 into this function, so I'm going to, right? It just gives me that value. There's no undefined, there's no discontinuity. That's a straight line. This is a linear function. It's a straight line. There's no issues with it. So plug negative 2 in. That's negative 14 minus, that's negative 17. Okay? Again, a quartic. This has no holes, no breaks in the graph. So remember, continuous means that you can draw the graph by putting your pencil down. You can draw the graph without picking up the pencil again, okay? So there's no breaks or holes in the graph. So evaluate this, plug in the 2. What's 2 to the 4? What's that, 16? Yeah. 16 times 6, 96, I think. Sounds about right. So negative 96. So that's pretty easy because you just plug values in. However, if a function is undefined at the x value for which we are finding the limit, we must simplify so that we can plug in the value. For example, if we want to find the limit as x approaches 3 of this function, I can't just plug 3 in because then I get division by 0. So what I want to do is I want to simplify this function using the fact that we are finding a limit to get to a point where I can plug something in. So I'm going to factor the top. So this is equal to the limit as x approaches 3 of, what does this factor into? 3 and 2. Positive 2. Yes. Okay. Now we see that this is also equal to the limit as x approaches 3 of, those would cancel and we'd be left with x plus 2. Okay. The only reason we can cancel those is because we're not talking about when x equals 3, because we can't cancel 0 over 0. We're talking about the limit as x approaches 3. So we're talking about being really, really, really close to 3. And so that's why we can cancel those. Because then it's some value over some value. It's 1 over, it's 1, right? And now I can plug 3 in, and so we see that the limit of this function is equal to 5. Okay, so make sure you keep your limit notation throughout until that time when you plug that value in, and then it just becomes that number. Okay, so let's go ahead and try this one. Again, I'd probably pause, do it yourself first, and check. So if I factor this, I have the limit as x approaches 1 of x plus 3 x minus 1 over x minus 1. So that's the limit as x approaches 1 of x plus 3, which is equal to 4. So we should get 4 as our limit there. Okay, that's about it for limits. The definition, the formal definition of continuity, we can link these two things together, continuity and limits. For a function to be continuous at a given x value, 3 things must be true. So you got to check for 3 different things. And those 3 things are, and using the example f of x and checking continuity at x equals c, right? Just some value. The limit must exist as x approaches c. So there has to be a limit that you can find. So left hand, right hand limit have to approach the same value. So it has to exist. The function must be defined at x equals c. So if you plug c into the function, you have to be able to figure out what that value is. And the limit as x approaches c must equal the function value at c. So it kind of seems, I don't know, maybe a little obvious, but that is the formal definition of continuity at a certain point, right? So the limit exists, they're approaching the same value, the function's defined at that value, and the limit and the value are equal to each other, right? That just makes the continuous smooth curve. So here, we would be checking, is this function continuous at x equals 1? And also, is it continuous at x equals negative 5? So like, which ones is it continuous at? So let's check this out. So x equals 1, I don't think there's going to be an issue plugging 1 into this function, right? So the limit as x approaches 1 of this function, I'm just going to shorthand write that, is if I plug 1 into this function, I get 6 over, what's this, 1 plus 11 plus 30? So 42. So I get 6 over 42. And f of 1 equals 6 over 42, because that's literally what I just did, right? And so the limit exists, the function is defined, and the two values are equal. So the function, so f of x is continuous at x equals 1. Okay? Now we got to check x equals -5. So the limit as x approaches -5 of the function equals, well, if I plug -5 in here, I'm going to have to double check the denominator. So -5 squared plus 11 times -5 plus 30. So that denominator does come out to be 0. So I'm going to continue working here, but we're going to know right off the bat that this is not continuous because it's not defined, right? It's not defined at -5. But I'm going to go ahead and show the limit anyway. So this limit as x approaches -5 is the same as the limit as x approaches -5 of x plus 5 over, let's see, can I factor this? X plus 5 times x plus 6. And so that's equal to the limit as x approaches -5 of 1 over x plus 6. So the limit exists. The limit exists, and so this is equal to, so the limit as x approaches -5 of f of x is equal to, at this point I can plug -5 in, so I'll go ahead and do that. So it's 1 over -5 plus 6, which is 1. 1 over 1, right? So the limit exists, it's equal to 1. However, we just saw that from the calculator, when I plug -5 into this function, I get 0 over 0 essentially, so it's not defined. So f of -5 is undefined, so f of x is not continuous at x equals -5. Kind of got cut off there. At x equals -5. So those are limits and continuity, and that's it for me. And we are, as I said, getting close to the end of the course, so not much more to do, but another pretty big topic to cover, and I will do that next time.